This is Growth and Decay Part 3. The last two videos you learned, one, how to graph exponential growth or decay using a word problem. You learned how to write the function, and now we're going to combine all of that together in this problem. It's very similar to the first problem that we did. So let's just get started. In 1981, the Australian humpback whale population was 350 and has increased at a rate of about 14% each year since then. Write a function to model population growth. So let's do that first. So I use my formula A of t equals the starting amount, the initial amount is 350. And I look to see whether or not it's increasing or decreasing, and it does in fact say increase, so that makes it very easy. I don't have to try to figure out what a word means. It says increase, so I know it's 1 plus the 14% being the rate, all to the t power. So if I simplify that, A of t would equal 350 times 1.14 to the t power. So I'm going to take my calculator and go to y equals. I'm going to put in the function 350 times 1.14 to the t power. Of course, x is going to be t, just like you learned in the last one. I'm going to graph it, but before I graph it, I'm going to go ahead and change the window. For part B, it says use a graph to predict when the population will reach 2,000. So if I go to my window, I'm going to change the minimum x value. This is over time since 1981. So I'm going to change it to -1, even though, why did it say -0? -1, even though I know that we're not even going to consider that because we're not going back in time. I'm going to just start out at 25. So 25 years later is what I'm predicting at this moment, or at least I know that I'll see it in my graph. The y minimum, I'll leave it at -1, and this y maximum, I'll leave it at 2,500 because I want to see when the population goes over 2,000 or around 2,000, and so 2,500 at least gives me a good enough window. So then I graph, and that's the image that I have. So all we have to do now is use our trace button to determine when the population will reach 2,000. This is going to be a more appropriate way to find it rather than using the table. So we're going to move until we get to 2,000. Use a graph to predict when the population will reach 2,000. Approximately 13.4 years later. So for part B, I just rounded this to the nearest tenth, approximately 13.4 years. So for part B, this is part A, we're going to say 13.4 years. Okay? And of course, we can go in and graph the information. I'm going to use my table in this case because I've got some whole numbers down here. Let me get back up to 0. We know at 0, if I plugged it in, that's our starting amount. So at 0, it's 350. So I'll be 200, 300, 350. Ta-da! And you made a prediction. So let's try the last one. Okay, a motor scooter purchased for $1,000 depreciates at an annual rate of 15%. Write an exponential function to model the value of the scooter. Then part B says, use the graph to predict when the value will fall below $100 and round your answer to the nearest tenth. So let's first start with part A. We write an exponential function. The word depreciates, it means it loses its value, so it's decreasing, it's a decay. So we're going to say A of t equals the initial amount, 1,000, times 1 minus the 15%. I'm going to write it as 1 minus 0.15 to the t power. So A of t simplified is 1,000 times 0.85 to the t power. I can't stress this enough. You cannot multiply these two values together first, because this is a multiplication step and you have an exponent. We don't know what it is, but there will be a value going there. So you will have to always do the number here to whatever power first, following order of operations, and then multiply by the initial value. All right, part B. Well, if we use our graph, let's plug this in. I'm going to go back to y equals, clear this out. We started at $1,000 and 0.85 raised to the x power, and window, I don't need to go up so high on my y because it starts at $1,000 and it's decreasing in value. So I'm going to start it at 1,500 just so I can see above where my $1,000 actually begins. And I don't know how many years it's going to take, but based on this graph here, it looks like we won't be going too much further past 16, so I'm just going to change it to 20. And there's the amazing graph. Go to your table. I'm going to go ahead and graph the points. We know at 0 years, we're going to be at 1,000. You should be able to see that this is declining, it's decaying, decreasing in value, and we were wanting to know when the value will fall below $100. So if we go to our graph and trace, we're looking for when it falls below 100. There it is. So at 14.2 is what we're going to round because it's the nearest tenth. So one space above it was at 103. When we hit it one more time, it's 14.2. So approximately 14.2 years. Okay, this is all for this video. So let me know if you have any questions. All right, have a good day.